Okay, let's talk about impulse and momentum. All right, so I'll start with like a little example here. So something that most people are more or less probably familiar with on some level is the concept of the magician whipping the uh, tablecloth out from under a set table. That's not a very nice table. Okay, there, a beautiful drawing. So this represents some massive objects. Let's give them mass. Each have a mass. And then the magician is going to whip the tablecloth at a very high velocity in this direction. And if he or she does this correctly, what you'll see is these objects more or less don't move. So how are we going to explain and understand this? And then the other side of things, right? So, if this happens really fast, these don't move. But if the magician pulls slowly, dot 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 dot, they will move. They'll move along with the tablecloth. So how do we understand that? So often people will say, well, this is a demonstration of Newton's first law, which is the law of inertia. And we say that since these objects have inertia, which we measure as mass, their tendency is to remain as they are, which is true, okay? And then we're often introduced to Newton's second law, which is often written like this, that if you apply a force to these things, to these masses, there'll be an acceleration. But you'll say, well, what's the difference though? Because we're applying a force in both scenarios, right? And then that force, of course, is the force of friction, the friction between the tablecloth and the bottom of these objects. Why does it matter? Why is there a difference if this happens quickly or if this happens slowly? And the secret is you have to understand the concept of momentum, and you actually have to think about Newton's law a little bit differently than the traditional way that it's written here. So let's think about this. We know from kinematics that acceleration is written as change in velocity divided by a change in time. Okay, so there's two components actually hidden within acceleration. One is that a velocity is going to change, and the other is that there's a time factor that's involved there. Okay, so let's rewrite Newton's law in a slightly different way. If acceleration is delta v over delta t, then we could write Newton's second law like this. Okay, write Newton's second law like this. And then what we can do is we can rearrange it to look like this. F t equals m delta v. Okay, so so if we rewrite this formula in this way, we can start to see that there's a little more to it than just simply, okay, these have inertia, so they won't move. And we realize that, if we pull this slowly, they will move. So why is that, right? So here, if we take a look at this, this is actually, as far as I'm aware, the way that Newton actually thought about his second law. Okay, and so let's look first at this force right here. Well, what does this force represent? This force actually represents, in this scenario, the amount of frictional force that you have here between these two surfaces. Okay, so the amount of frictional force. Now that's set by nature. We know from previous experience that that frictional force is equal to mu times the normal force. So looking at it in that sense, we've got gravity pointing down, we've got a normal force pointing up, and we say the amount of frictional force is some coefficient, which is basically based on the characteristics of the sheet in the bottom of this object. So with, to make this magician's chances greater, you should get a very smooth tablecloth, and usually dishes are made of glass, so they have a pretty, slippery bottom. So the coefficient of friction should be pretty low, all right? Pretty low. And there's two sort of competing things here, right? If you use a lot of mass, you get more force. But if you use a lot of mass, you also have more inertia there, right? So this is kind of like relationship that you got to think about. We'll see, maybe we'll see if that matters a little bit later. So this is the frictional force. This is what is capable of making those plates move, okay? And the interesting thing is that is set by the nature. So that is something that's locked by the system, right? So no matter how fast I do this, the amount of frictional force that's applied here is the same. Doesn't matter if I do it fast or slow, the amount of force is the same. But look at the second part of this little equation. That's the time factor. So if I do this in a really short amount of time for a given force, then whatever's happening over here is smaller. If I do it in a really long or high amount of time, what's happening over here is greater. So let's look at this component now. This is mass of, the objects on there, so the plates and stuff, right? Mass of the objects, mass of the plates, and whatever, right? This can't change. You can't change the mass mid-thing. I mean, the mass of an object is the mass of an object. So if this is set, then and this is set, essentially by changing the time factor, we can move this up or down. How much change in the velocity of this object there will be. So the faster the magician can whip that out of there, the less velocity change we're going to have on the other objects. So if he pulls really slowly, you have that low force for a long amount of time, you can cause a large change in velocity. But if he's very quick, he'll cause almost no change in velocity. So it's this interplay between the inertia of the objects, their resistance to change in their motion, how much force we apply to the bottom of them, and then for how long we apply that force for. So this is how we have to think about it. It's not just inertia. It's not just this is a demonstration of inertia. You have to think more about the bigger picture and about what's actually going on kind of in a more nuanced kind of way. So what are these things called? Well, Newton would have said this. He would have said that impulse is equal to a change in momentum. So now the next question is, well, what is momentum? So let's introduce that, and then we'll come back to this and talk about how this applies to that. Okay? So the first thing is momentum itself is defined as this. Momentum, which in physics we use as a p, okay, so a p is the symbol for momentum, is just an object's mass times its velocity directly. No delta there, just its mass times its velocity. So for example, a 100 kilogram object moving at 10 meters per second has 1,000 kilogram meters per second of momentum. So Newton referred to momentum as the quantity of motion. Quantity of motion, a way of mathematically measuring motion, right? And that's not very interesting on its own. Okay, fine, like an object has motion, big deal. Just remember too that this is the inertia part, and also remember that velocity is relative. Okay, so momentum's relative as well. In other words, if I'm traveling alongside a bus, and the bus and I'm in my car, and the bus and I are traveling at the same velocity, the people in the bus and I do not have like a momentum relative to one another, assuming we weigh the same mass, right? If we're going the same velocity. Actually, we have no momentum relative to each other if we're traveling at the same speed, because there's no difference in our velocity. So there's a relativity aspect to this. We don't really need to fixate on that concept. But if you're traveling the same speed as an object, essentially the velocity difference between you is zero. So the momentum difference is zero between you. And that matters when you start to get into the concept of collisions, right? You can't collide with something that has the same velocity as you, right? If the velocities are in the opposite directions, then yes, but then they wouldn't be the same, right? They'd be in opposite directions. So we get to collisions, keep that in mind. Okay, so if we have an object sitting still, okay, its momentum equals zero, okay? If we want to give it a momentum, right, we have to apply a force to it, and that force has to act for some amount of time. This should make common sense to you. If you apply a force for 0 time, nothing's going to change about this. If you apply a force for some amount of time, you'll get this mass m to get some velocity, right? So there's going to be a change in its velocity from 0 to some higher value, okay? This part of it, okay, the thing that can cause a change in velocity is a force acting for a time, force times time, Newton called this impulse. Okay, so we see here that this isn't momentum, but this is delta P, right? It's the change in momentum. Since I started at 0 here, m delta V will actually be my momentum, but that doesn't necessarily have to be true, right? This could have already been moving and I could have pushed it more, right? So then it would be the change in momentum. So impulse causes a change in momentum. So the question then is, what units would we be working in, right? So let's just see if it all adds up, right? So force times time. Well, force is measured in newtons, and newtons are kilograms meters per second squared, times time measured in seconds gives us a unit of kilogram meters per second. So the units of impulse and the units of momentum are the same, okay? The difference is when we're just talking about a straight momentum, okay, impulse isn't factored in. I mean, you needed an impulse to get there. We're just looking directly at that object's current momentum, not about how it got there. When we're talking about how we're changing momentum, we're changing motion, now we need kilogram meters per second, okay? And if we just take this formula, we divide this by T, then we go right back up and over to newtons again, right? So force is equal to m delta V over T. That should make sense. Meters per second squared, okay? So this is how we have to think about this scenario, okay? So impulses cause change in momentums. So hopefully that kind of gives a little bit more insight into the explanation behind how the magician's cloth whip trick works. I think it's a little dishonest to just say, well, it's because this has inertia that it doesn't move, right? There's more to it than that. There's definitely more to it than that. Friction plays a role. The time factor plays a role. Okay, let's move on. So now let's talk about conservation of momentum. And essentially, this is just this law of nature that in any collision between two masses, the momentum of the system is always conserved. Okay, you can see this with something like a Newton's cradle. That's the hanging balls. What you'll find on any video about Newton's cradles that's out there that you watch, whatever happens in this direction happens out in that direction. So if I let one ball fall in, one ball will leave out the other end. The MV before the collision is equal to the MV after the collision, okay? It's just that it's moved to a different object in the system, all right? And anything you can think of can be explained this way. I mean, let one go in this way and one go in this way, and they'll bounce off of each other, right? Let two go in, two go out. Let three go in, three go out. Let three in one side and one in the other, and they'll switch. But the momentum will never change, okay, in that system. Eventually, it'll like wind itself down, which is another thing that's going on. That's a loss of energy to the environment. But until all that energy is gone, the law of conservation of momentum holds true, okay? We'll talk about it a little differently. We'll talk about two types of collision first, and then we'll talk about how we mathematically look at collision. So the first type is an elastic collision. So this is when objects collide and bounce off each other, like the Newton's cradle. Newton's cradles are elastic collisions. There's bouncing. So you might see this, if you say had two, I don't know, two solid steel marbles that collide with each other before, and then after they would bounce off and be traveling in the opposite direction. But P would be equal to P prime, right? The before and after would still be equal, okay? So let's look at this. Elastic collision. What we could say is we could say this is mass 1, and we could say that this is mass 2, okay? And if we look at the momentum before, this is what it would look like. We've got M times v of this object plus, right, m times v of the other object. But now remember, the velocity is in the opposite direction, right? So actually we consider this to be, because momentum, and momentum is a vector value, sorry, I forgot to mention that, it's a vector value, the direction matters, right? And what we'll find is that the after effect, right, so this m now here will have a negative velocity, okay, or just move that over, put it there, plus this mass, right, times it now having a rightward or positive velocity, okay? So it's kind of an easier way to write that. It's just this, m1v plus usually big mv, sorry, mv, we'll just do it like that, plus big mv equals mv prime plus mv prime, okay? And let's just put a little a down there just so we know that those are the same, okay? So this is kind of a generalized law, and all it's saying is this: the total system momentum, so total P before a collision, always equals the total P after. All right, these are always equal. So momentum plus momentum equals momentum plus momentum. I guess a simpler way is you could just call it P1 plus P2 equals P1 prime plus P2 prime. So that's just nomenclature. What really matters is that you understand the concept here, all right? This is the full formula for solving really any momentum question, at least linearly, right? We'll call this linearly. These two objects are like just on a surface. Later we might do it in more dimensions, but for now, just linearly. This can basically take care of any situation, okay? So this is for a full formula for a fully elastic collision, okay? Now we could have another type of collision. Let's say we have two clay balls coming together, okay? And then after, they stick, okay? So there's two clay balls, and we would call this an inelastic collision. However, it's still going to obey the laws of conservation of momentum. And we could say if these masses and velocities are identical, then the momentum before would actually sum to zero, and the momentum after would actually sum to zero. That doesn't mean that individual momentums can't have a value. It just means that the system in total, and if these are all equal, would be zero, okay? So you still have motion, but because they're vector values, they cancel out, right? So you end up with a zero value, and that's what your negatives are showing you there. Now in this case, with an inelastic collision, you still kind of have the same idea. You have, let's call this little m, call this big M, okay? It has a velocity, it has a velocity. So we still have the same kind of starting scenario, plus big M, let's just go big V, except now we have a slight change in how we write the second part, right? Because now we have one new mass, which is M plus M. We actually get this, M plus M times nu V, okay? So V prime. So there's just a subtle difference when you're talking about things that stick together versus things that bounce off one another, okay? It's just another sort of way of, basically it's putting these two together, M plus M, and realizing they have the same velocity at the end, the identical velocity.